many people don't realize this, but a IC engine's about 35% efficient. That means the power coming out of the fuel that you provide, only 35% of it actually gets through the motor. A lot of it's heat. That's why you have radiators in your car and you're cooling the engine all the time. But when it comes to an electric motor, it's 90% efficient.
Welcome to another edition of HYDAC on Tap, where we tap into the expertise, nearly 60 years of expertise here at HYDAC. Today, we're going to talk about hydraulic efficiencies. And who else better to talk about that than our dear friend, Chris Kolbe, Senior Vice President of Marketing and Sales here at HYDAC. Welcome.
Thank you for having me.
Of course. So tell me about this term hydraulic efficiencies. Let's dive right in. What does that really mean? I hear that term a lot at HYDAC. What does it mean and why is it so important?
Yeah, it is. It's really the buzzword now of the industry, right? And I think there's a lot of misconceptions on what it really is. So I think it's important to define what we mean when we say hydraulic efficiency. And really, it's as simple as the power coming out of the engine or the electronic motor that's driving the pump, so that power coming in versus the actual hydraulic or mechanical output you get from the device you're driving, the actuator. So, for example, what your engine's putting out and how much power you're getting out of a digger if you're using an excavator. That number, that efficiency, is the efficiency that we call hydraulic efficiency.
Oh, okay.
And it's important for several reasons, really. It's in today's climate and in today's environment, energy costs are high. And anytime we can minimize the hydraulic losses and improve efficiencies, it's a savings on money. So that helps your total cost of ownership. And in addition to that, a lot of times when you get more efficient, you get more compact. So that really helps when it comes to the real estate that you're using up on the machine. And of course, space is of a premium because everybody wants to make a more compact machine. And then there's the carbon footprint. So the more we can do on energy savings, the more efficiency we can get, the less heat loss that we get, the better carbon footprint we can provide for our customers and then ultimately the end users that are using it. I think that's coupled with the initial machine cost. That's really the benefit of having a real strong or increased efficiency of hydraulics.
You mentioned total cost of ownership, and I know a lot of our customers have told us that that's like one of the most important things facing their, as a challenge facing them, whether it's an end user or a machine manufacturer. Total cost of ownership is key. What do you see? Like, what is the return on investment? Is it less fuel? Is it less? Is it longer battery life? What is the major return on investment for our customers and machine manufacturers?
Yeah, you're absolutely right. A lot of times the end user that's using these equipment, really the total cost of ownership was really a couple different factors that factor into that. Number one is the initial machine cost. That obviously is part of that cost. But then it's the ongoing cost of maintaining and operating the piece of equipment, and how much efficiency and productivity you get out of it, right? So those are really the three areas that you're looking to improve, and they factor into that cost of ownership. So the reason why it's so key and hydraulic efficiency, it's both for when you're using an IC or internal combustion engine, because ultimately the higher the efficiency, the less fuel that you'll need to do to make that same level of output, okay? And sometimes we can make the hydraulics more efficient, which allows the machine to be more productive. So not only do you burn less fuel per hour, you're actually getting more work done per hour as well. So that's a double whammy where you can improve both. Now, when it comes to a machine that happens to go EV or electronic, where we're removing the IC engine and we're using an electric motor driven by either a hydrogen fuel cell or a battery, then efficiency becomes even more critical, because typically when you have an IC engine, a lot of the losses in that energy is actually in the engine. So for example, many people don't realize this, but a IC engine's about 35% efficient. That means the power coming out of the fuel that you provide, only 35% of it actually gets through the motor. A lot of it's heat. That's why you have radiators in your car and you're cooling the engine all the time. But when it comes to an electric motor, it's 90% efficient. So that means that when it comes to hydraulic efficiency, it has much greater impact on the actual output. So for example, if you improve hydraulic efficiency by 20% and you do it on an IC engine, typically it means the ultimate efficiency of the whole system will raise from, let's say, 18% to 21%.
Okay.
It's an improvement.
Yeah, that's not too bad,
but mild. Now,
Yeah.
if I do that same thing on a electronic-driven, battery-operated machine,
okay.
the impact is much greater. It goes from 46 to 61, which is a 15% improvement versus a 5% improvement. So again, that makes the cost savings. So what does that really mean in the end?
Yeah.
So on the IC engine, it means less fuel.
Okay.
Less fuel consumption, right?
Yep.
Which has a return on the investment. However, when it comes to electronic-driven vehicles, battery-operated vehicles, that could mean 6 hours of runtime for the battery, all the way up to 8 hours runtime for that battery. Or if you still just want to operate at 6 hours, you can significantly reduce your battery size, which could save up to, $13,000 of battery costs, because the battery is the most expensive part of the machine.
So there are different benefits based upon
They are.
what your goals are and how you're using
Yes.
the machines.
And it really comes to the duty cycle of the machine and how the end user is doing it.
Okay.
So it gives the OEMs flexibility, either save money on the initial cost of the machine or give them more runtime when it comes to battery life.
I thought the hydraulic industry has been fairly mature lately, and
Yeah.
I didn't think there was that much more room for, advances in technology. But what is the HYDAC approach that leads to some of these benefits?
Well, I think that maturity has been around for a while. Because when you look back at the hydraulic industry, it's been around. I mean, HYDAC alone's been around 60 years. Hydraulics has been around since the initial excavator that they made hydraulic back in the early 1900s. So, the technology is 100, 110 years old. So some people think it's getting to a level of stagnance. But in reality, we have a lot more room for improvement. There's a lot of innovation. And now with the battery-driven vehicles, there's much more demand for efficiency, which allows us a lot more opportunity to put more technology into the hydraulic system, both with the electronic controls, coupled with some of the new technologies and materials that allow us to come up with different components and different system architectures to make the machine a lot more efficient. And that's really, really key. So it's not dead. It's not stagnant. There's a lot more room for improvement.
And tell me about the HYDAC approach. You and I had talked before about different levels of operations and different approach that we have, whether it's component or other focuses. We're more of a partnered and solution-driven approach, correct?
Yeah, I mean, when you work with HYDAC, we really want to view ourselves as a consultant, as a partner, as an extension of the engineering staff. So when we come in, we want to learn about the challenges, what they're trying to accomplish, what some of the pain points that they have, to really understand what they're trying to do with the vehicle and how we can increase the value of that vehicle. And when you take that approach, usually it boils down to 3 different ways we can help, okay? One is a component level, which typically is pretty quick to do because it's simply substituting this part for another part that might be an improvement. The second way would be a sub-function. So let's say you're trying to lower something. That function that's lowering, we'll take a look at maybe 5 or 6 components that go into that subsystem. How can we reconfigure it to make it more efficient? And then we can take a more holistic approach where we're looking at the overall system architecture and how the whole design of the machine is, and take an approach like that where we can improve efficiency. Now, those 3 different approaches have different timetables, different engineering efforts, but also different impacts. So at the component level, it's the easiest to do, but usually the lowest impact. When it comes to the subsystems, typically a little bit more work, but more impact. And then finally, when you take the holistic approach, that's where you're going to get the biggest bang, so to speak, for your buck.
So let's talk about the first area, the components. What are some of the key factors that you see that there are in selecting the right components.
Yeah, I think this is really key. So the biggest hindrance to efficiency when it comes to hydraulics is pressure drop. Okay, what do I mean by that? Well, anytime oil flows through something and there's a resistance, that resistance creates heat. And that heat just simply means loss of energy. So anytime something gets hot, you're losing energy. It's not as efficient. So one of the keys is, am I selecting the right size? And am I driving the right component selection to minimize that pressure drop? So I'll give you an example. So you might have an application where you're trying to, let's say, you have a clamp on the end of an excavator and you're trying to move it back and forth.
Okay.
It takes a lot of flow. Okay. If you have a small valve in there that's not
Sized properly?
yeah, and has a lot of pressure drop, that can create a lot of heat, which really reduces your efficiency. So, HYDAC has a number of different valves where even though the size, it still fits in the same area, but it opens up greater, gives a bigger flow path for the oil. Therefore, you get less pressure drop. And that can mean it can cut down your energy losses in half by reducing the pressure drop in half. So that's one example. Another example is, let's say on the end of an excavator, you have a rotary brush. So that needs the most amount of flow. Usually that attachment has more flow than any other. Well, we have some valves that have a two-stage where you can actually, the first stage can give you a nice fine metering, but the second stage then opens up much greater, reducing that flow path and again, increasing efficiency.
Okay. That's excellent. So you also mentioned subsystems. What are you looking at when you're looking at that category? Yeah,
again, you think about a subsystem, that's really like a sub-function on a vehicle. So you think about one function could be steering. It's holistic, right? It's the components that are used to drive that one function. Another function might be lowering. So I always like to use an example of an aerial work platform. I think everybody kind of seen product like that, whether it be on a job site, painting someone's house, working on windows on a commercial building. Those AWPs have a large basket on the top where someone's sitting,
yep.
And then you lower it, right? So in your head, you're thinking, I don't need any power to do that. Gravity should be able to lower it. I have weight. I have a person on top. All I really need is to fine meter that thing down, put it into place. So that's a function that has a lot of room for improvement because traditionally we had to put a device in to ensure that if a hose broke, that it wouldn't fall down. Okay. But when that device is there, you are restricted, so you actually have to push that basket down using hydraulic power.
Rather than, as you mentioned, gravity.
Letting gravity do the work.
Right.
So how do you tackle that function differently so that you can eliminate that power that you're driving down and creating more work than you need to? So what we would do is we'd put in a electric PO check or counterbalance valve that now we can move electronically out of the way, open that flow path more. So now we can let gravity do its work and let it come down by itself because we're not relying on the oil to push it down and drive the device down.
So this is what you talked about, being more of a consultant with our partners and with your customers, making sure that we find out how they're using the machine to help them provide solutions like that.
Absolutely. So this is where you're trying to look at use cases, right? And you're trying to figure out how is the end user using it. And the other thing is really understanding where those pressure drops, where those pain points are.
Okay.
So a lot of times we'll come into a customer and we'll say, can we hook up a bunch of transducers on your machine and really get an understanding of where your issues lie? So we'll instrument the machine up, we'll take a whole bunch of data, and we can find out where there's opportunity to reduce some of that pressure drop that we're seeing in the system. So, and that's how on the AWPs, that's where we found that most of the energy loss was in that lowering function because the energy wasn't really needed to do the work, but just because of the sub-function design, we were forcing it to do the work. So again, we can usually do that fit up on site, or we can come up and put that instrumentation in on the vehicle at the customer location. Or we actually have a tech center in Chicago where we can actually bring in the vehicle. we can fit it up and run those tests. And then if we want to, we can put a new subsystem in and do the test again and show the efficiency gains through the data and track it so you can quantify it, what it's going to mean to the end user and to the OEM.
That's pretty powerful. So that's probably most customers would love to see that data.
Yeah, and I think this is the key, is because if you have the data, then you can really quantify the business case to the end user and saying, this is really the efficiency gain I get from a cost savings from either fuel consumption or from battery life. And the other thing is when you reduce the hydraulic heat in the system, you need less cooling.
Oh, okay.
So you think about a lot of times your coolers are sized to get rid of that heat that you put into the oil. Well, if I can minimize the hydraulic heat in the system, I can start to shrink up that radiator or that cooler, right, into a smaller package, which helps both in cost and then, like we said before, most space. Space is always on a premium when it comes to vehicles.
Especially for the manufacturers trying to design new vehicles.
Yeah, it's one of their biggest challenges or pain points. Absolutely.
Excellent. So let's talk about the third part. You had mentioned architecture.
Yeah.
I think you mentioned it, or I heard this, that's probably the most impactful area that we can have an impact on.
Yeah, it really is, because if you think about it from this point, you're not just changing one or two little parts to try to improve it. We're taking a whole white, clean piece of paper approach to it where we can look at what we're trying to do from a duty cycle standpoint and what work needs to be done, and we can configure a system that is optimal for it. So yes, it takes a redesign, but that's where we can put all of our new technologies in and all the efficient approaches that we have into it at a system level. So let me talk a little bit about what that really means.
Okay.
First, I think when it comes to battery-operated vehicles, there's a lot of opportunity because traditionally we had a IC engine that was, going, rotary driving the pump and using for propulsion to move the vehicle, right? So that means the pump had to be located next to the engine, right? And it had to go to the same speed that they needed for propulsion. So if you're driving down the road and you needed to go 30 miles an hour, there was a certain level of RPM that was required. Therefore, the pump was spinning even if you weren't even using it, okay? Now, when you go with battery operated, you decouple that. So now your hydraulic system is separate from your propulsion, which means now you have the opportunity to drive the motors and the pumps at the speed that you actually need to do the hydraulic work. So that's number one. That decoupling allows us to put the pump anywhere and drive it at speed that the hydraulic demand requires. Second thing is we're free to use more pumps, and we can place those pumps in different areas. So why is that important? Well, traditionally you have a single pump system, which means if you have multiple functions, so let's say I'm going to use an example of like a terminal truck. So a terminal truck has steering.
Okay.
And then a terminal truck is one of those you see in the yard. So they pick up, let's say, a semi truck and they move it around or semi back into the semi in their trailer and they're moving it around the yard.
They're moving the trailer around the yard. Got it.
So they back up to the semi trailer and then they lift it up. They lift the back end up so that they can move it around the yard. So that's really two different functions. And when you look at the steering function, which is almost continuously being used, It runs only at about 1,500 PSI. However, when you're doing the lift requires a lot more pressure because you're lifting that heavy load of the trailer up. So you have to spin the motor all the time, but you also need to have enough pressure for the lift. Anytime you have a big differential in pressures that are required to do one function versus another, if they're running off the same pump, the pump has to go to that higher pressure, which means if another subfunction's using it, that delta in pressure goes into heat. So one of the keys that you can do in many instances is you can use two pumps. You can have one pump that's running one function at a low pressure and another function running at higher pressure for the other work function. So you separate the two. Therefore, you don't get nearly as much heat because you don't have to have that pressure differential to operate both functions.
So that's where the decoupling comes in as a huge advantage.
Huge
Multiple
advantage.
pumps, less heat, and
Yeah.
goes back to the space issue, less cooling.
Absolutely. So then again, you're running less space. Here's the other thing is a lot of times when you go to sizing a motor to run those functions, typically people, let's say you had a 50 horsepower engine. They're like, okay, I need 50 horsepower now to drive my hydraulic function. In reality, if you can do some of these optimizations, like I talked about, where you're running different pressures for the two different functions, you can take and really size back that motor. So, we have some real world examples where we've taken something that, let's say, they thought it required a 70 kilowatt motor,
Okay.
and we were able to reduce it down to 30 kilowatts by separating those two functions by two different pump pressures.
So again, more cost savings just on the different components needed.
Yeah, so that goes back to your total cost of ownership. Like we said, there's the initial cost, so we were able to size that motor down. Then there's the ongoing energy cost. We're able to consume that smaller motor consumes less battery, less electricity, right? So you save on that charging cost, or you get longer life out of your battery. So that cost of ownership really gets impacted in two different ways.
All really, really great benefits. So you mentioned this this real world example of this terminal truck, for example. So what kind of percentages, what kind of efficiencies are we talking about? Is there like a standard or a
it's always a little dependent on again what those two different pressures are. But let's talk in generalities, right?
Okay.
So in generalities, we can usually save up to about 40 to 50% on efficiency, especially when there's a pretty big gap. Let's say more than 1,000 or 2,000 psi between the two work functions. We can save up to about half that power because that delta is taking away the rest of that energy.
Got it. So you would say electrification is a big part of this too, in that it's helped us decouple the different functions.
Yeah, here's the great thing. We know that battery operated vehicles are growing a trend, right? And but the thing that's been very impactful that we've found is that when we've done the efficiency gains for the battery operated truck, not only have we reduced and improved the operational and reduced the battery size, but the hydraulics become so much more efficient and so much smoother because we're actually simplifying them when we decouple it, that we end up taking a lot of that technology and that approach back to the same version that has the IC or the internal combustion engine. So a lot of times we will find out what really works well with the battery operated version, and we'll take a lot of those ideas and put it back into the IC engine as well, because in the end, the operation of the machine is smoother. Usually we gain in productivity, and then we're also improving the fuel consumption.
So where should a customer begin this process? What areas do you think they should be focusing on?
Well, again, I like to take a step back and say, looking at my component versus subsystem versus system, holistic system architecture approach. And depending on the scale of the redesign you want and the timing that you have, if you have a little amount of time and you don't have a lot of resources, I start looking at the component level. So if I'm looking at the component level, the first thing I start looking at is heat loss. Where do I have heat problems on the vehicle today? So for example, is my valving sized right? Are my hoses restricting? Do I have a lot of elbows in the system? There's some very quick things you can do and to find out, is the energy coming out of the pump, that pressure coming out of the pump, actually getting to the work function?
Like you said before, like some of that, the traditional methods was very small percentage.
Very
like
small
30%.
percentage. Yeah, exactly. So what we typically do would put pressure on the pump, measure pressure at your actuator. If there's a big pressure loss, that's an opportunity for improvement, okay? So I would look at that. Now, if you have a little bit more time and a little bit more resources, then what I would start looking at is what are some places where I have potential energy that I can use. So where am I doing a gravity lower? Where can I recapture energy? Let's say I'm braking or anything that I can either store that energy back into the system or I can let gravity do some work. Those are other opportunities that I would use. So again, depending on the scope and scale that you have, I think the key is getting someone like HYDAC involved that understands how to instrument up the vehicle to understand where those heat losses and those potential pressure drops are really sticking out.
So let's just talk a little bit more about pressure drop. I mean, isn't that just part of a standard hydraulic system? I mean, you're going to have some type of pressure drop, right?
Yeah, I mean, ultimately, to have controllability, you need pressure drop because ultimately, like a valve, kind of like when you turn your faucet on, if you want to meter the water going through your faucet, right? You need there's a pressure there, right? There's a loss of pressure. There's more pressure coming in that's coming out of your faucet, so that valve's going to have some pressure drop.
That makes
there,
sense,
right?
yeah.
But what's important is when you're sizing that component is to understand what is the maximum amount of flow that you need and what is the smallest amount you need, and picking a component that has a good full range and controllability through it, but can open up wide enough to give enough flow path so at those high functions, you have less pressure drop. So here's a perfect example. If you're using a clamp, let's say on an excavator, when you're picking something up, like let's say you're picking up this glass, you want to go really slow right before you touch it. But when you release it and you want to get back to full position, you want to go really fast.
Okay.
Right? So here you're doing small metering, so you need a very small, high resistance to get that small flow rate. And then so when we're selecting that component, we want to be able to have a valve that can have a very wide opening and still be able to have that fine metering on the end. And that's where we can help in that selection process. And what's interesting is that factors into some of the designs that we do on the product. So when we're designing that valve, right, if we know that that's kind of the flow rate that you need, we can put some different features into the valve that allows for that fine metering really well. So, for example, we might put a small notch in an area that gets that fine metering, but then it has the full opening to reduce the pressure drop at those high flows.
So again, it goes back to understanding your customers' needs, the functionality of the vehicles that you're working with, and then looking at all the different factors there's a lot of different factors that impact the design.
And this is why it's so important to collaborate with our customers and get involved early in the design process.
So you're not just trying to sell them a component.
That's exactly what we don't want to do, right? So what we want to do is if we understand their problems early on in the design process, if we build that collaboration and kind of consultative process, when they're first looking at the vehicle and they're like, hey, I got a use case where I need a lot of flow for this clamp, we can help in the design of our product to really help the efficiency of the overall machine. But we can't do it. It's much harder to do it on the back end than if we're involved early collaborating with the customer on the design end.
Yeah, you can affect the design.
Yeah, essentially their design affects our design.
Got it.
And that's where the collaboration really happens, and that's really where you optimize the component design. Is if we can get our component design driven by what the OEM is trying to do with the vehicle.
But I guess if you had to pick one or two takeaways for our customers to really zero in on, what would you say would be the most important?
Yeah, I think a lot of times people have not looked at optimizing or really making any adjustments to their hydraulic circuit in a long time, right? Because it's worked fine the way it has for a long time. They put coolers in, it's coupled to heat.
It's a lot of work to make changes.
So they were focused on other things on the vehicle. Take the time to reanalyze your hydraulic system. Because nowadays the technology has changed, and with electronics and sensing, we can do a lot of things different than we could before. And we can get some of these little wins, whether it's a component change or whether it's simply the approach on using gravity to help. If we do that, we can build momentum, and that momentum then can help further optimize the machine. Those little wins add up to some big changes and big improvements over time. So I think, again, you're going to need help. Most customers don't have the sophistication to really take a good analytical look at how they can improve the efficiency of the hydraulic circuit. This is where someone like HYDAC that has those experts, that has those tools, that has those facilities, and then ultimately has the components, can really analyze and really help that customer through that journey. Because again, like a lot of those improvements, it's about planning something, doing, measuring, and then communicating that to your customer.
And a lot of those efficiencies that you've mentioned does equate to savings, whether it's energy, whether it's total cost of the ownership or total cost of the manufacturing process.
Yeah, and I think this is the key is they can go to their end customer and say, I can improve your total cost of ownership. Like I said, better selection of product, kind of reduce some of the cost, initial purchase cost, and even if you can't reduce it, you can certainly help the total cost of ownership by less energy consumption. And not only is that green as far as dollar savings, it's also green as when it comes to the environment and the carbon footprint. So it's a win-win in multiple areas.
I like that. So green in sustainability and green in
payback,
the currency.
Yeah, everybody needs an ROI, right? And that's an ROI for an end user to buy a new piece of equipment, because if they can reduce their total operating costs, that energy saving on fuel or electricity can pay for itself in the course of a year or two, which helps drive new sales into the industry for our OEMs.
Excellent, excellent. Well, you heard it here, folks. Again, thanks for joining us today on this episode of HYDAC on Tap. Learned a lot about efficient hydraulics and how it can affect machines and manufacturers, both and the end user as well. So really appreciate you coming in, Chris, to talk to us.
Thanks for having me.
Of course.
Thanks for having me.
Remember to like and subscribe on our YouTube channel. You can also follow this podcast on your favorite podcast streaming program, whether it be Amazon, Apple Podcasts, Spotify. Don't forget to hit the bell, and you'll get notifications on new content. And we'll see you next time on another edition of HYDAC on Tap.